we're going to take a look at another type of addition reaction to alkenes, and this one is called an ozonolysis. And basically what we're doing is adding ozone to alkenes. Here we have ozone O3. It's typically produced in the lab by taking oxygen, O2, and passing an electrical current through it, and then used from there. But if you want to look at the structure of ozone, we have 3 oxygens bonded together. Like this. Our central oxygen carries a positive charge, and this oxygen on the end here carries a negative charge. And what we can do is we can add ozone across this double bond. Our electron movement here, we can think of a lone pair on the oxygen coming down and bonding with this carbon of the double bond. Then that would send this pi bond up to this oxygen, and then from there we can push these 2 electrons over onto the positively charged electron deficient oxygen. When we do that, we get these carbons that were part of the alkene bonded to the ozone. And this product is called a cycloaddition product. Because we added the ozone across the double bond in one step and made a cyclic molecule. Now this cycloaddition product isn't stable, and it rapidly undergoes a subsequent reaction to form what's called an ozonide. And for those of you that are interested, we can look at the mechanism for that later. But what happens is this then undergoes a conversion to give you this ozonide. And just to kind of keep track of things, here are the 2 carbons of the alkene which end up here. Here are the other 2 carbons of the alkene which end up here. So during this transformation, this carbon-carbon single bond actually got split. Now here we have our ozonide, and just the ozonide in and of itself isn't all that useful, but what we can do is do some sort of workup, either oxidative or reductive, to get to more useful products. And for this example, just to continue on, we'll do a reductive workup. And what we're going to do for that is we're going to use DMS, which is dimethyl sulfide. And just to help us keep track of things, I'm going to go ahead and draw in the hydrogen on these carbons. So once this ozonide is subjected to the DMS step, so from here what we'll think about is how this DMS can break this ozonide down. And it may not be quite this simple, but we'll just use this to track our electron movements here. Sulfur with some lone pairs, and we want to think about how we can break apart this ozonide, and just to kind of track electron flow, I'll show this sulfur bonding with that oxygen, pushing these electrons up to form a double bond, these electrons down to form a double bond to the oxygen, and then these electrons over onto the oxygen. So if we draw the products from this, we end up with, on this side, a carbon-oxygen double bond, hydrogen, so that's an aldehyde. On the other side, due to symmetry, we end up actually getting the same thing. And then we end up with sulfur bonded to the oxygen. And this actually ends up O minus, S plus, and this is a byproduct called dimethyl sulfoxide, or DMSO. And what we want to do really is be able to look at a starting alkene and see the reaction conditions, and from there predict the products of the reaction. So without really thinking so much through the mechanism, we can predict the products based on the ozonolysis step and the type of workup step, be it reductive or oxidative. So in this case, here we have an alkene that we're starting with. We're subjecting it to ozone followed by DMS. And the net result of what happens here is you're getting cleavage across this double bond, and each of these carbons, the one on the left ends up double bonding to an oxygen, and the one on the right ends up double bonded to an oxygen. So drawing the products, especially from this reductive workup, is pretty straightforward. For the product on the left, we have our methyl groups still bonded to that carbon, and this carbon gets double bonded to an oxygen. So this product of the reaction is a ketone. Then on the other side, we do the same thing. We have our carbon, hydrogen, methyl, and then this carbon, that also gets double bonded to an oxygen. Since this alkene carbon had a hydrogen on it, the product here is an aldehyde. So again, that's a reductive second step. Now we also have the option of an oxidative second step. And we'll look at the same starting alkene, but now we'll use ozone, and for the oxidative workup, water and hydrogen peroxide. We're going to track these carbons of the alkene the same way. Okay, and for this reaction, again, we're going to be cleaving the double bond. On the left side, we just have carbon groups, nothing changes. So this carbon will just become a C double bond O, and we still will have the methyl groups attached. The main thing that changes in an oxidative workup is when you have a hydrogen on your alkene carbon. So this hydrogen will get oxidized to an OH group in the product. So now when we draw the product for this, our second product, we have our carbon. It still has a methyl. We still get the double bond to the oxygen. The difference is now instead of getting bonded to a hydrogen, this becomes an OH group. So our product for this is a carboxylic acid. So nothing changes if the carbon of the alkene is just bonded to other carbons. The only time something changes is when the carbon of the alkene is bonded to a hydrogen. So if you're interested, we'll take a look at the reaction mechanism. And the first step we already saw, formation of the initial cycloaddition product. We'll just draw that again. These electrons come down to form a bond with this oxygen. These electrons go to this oxygen, and then we push these over onto the positively charged oxygen. So this gives us our cycloaddition product with the 3 oxygens present. Now the next thing to keep in mind is that oxygen-oxygen single bonds are pretty weak, so they're quite willing to break. And what's going to happen here in order to go from this intermediate to the ozonide, what I'm going to do, I'm going to involve the lone pair electrons on one of these oxygens. And I'm going to push these down to form a carbon-oxygen double bond. At this point we can't have 4 bonds on the carbon because remember, we do have hydrogen here. Let's just draw those in. So from there, I'll actually push these electrons to here. That'll give me a carbon-oxygen double bond. And then we can't have too many electrons into the oxygen, so I'll break this oxygen-oxygen single bond and put a lone pair onto that oxygen. So this gives me 2 different products. I end up on the left side with an aldehyde. Then on my right side, I end up with a double bond to an oxygen because I moved these electrons down, but this is still single bonded to the other oxygen. This oxygen is negative. This oxygen is positive. This is called an aldehyde oxide. Now in order to see what happens next, I'm actually going to flip this aldehyde over. So no reaction here, we're just reorienting things to see how the electrons move a little better. Do that. This. We still have this. Okay, and then what I'm going to do, I have this oxygen, which is nucleophilic, this carbonyl carbon, which is electrophilic. So I'll form a bond here. These electrons come over and attack this carbon, and then that pushes these electrons up onto the positively charged electron deficient oxygen. So now when we draw all of this out, I'll start here. I have that oxygen, that one. Now I have a single bond. There's my carbon, hydrogen. Here I have this new bond to this oxygen. And then this still has the carbon-hydrogen attached. And then we have a bond from this carbon to that oxygen. And this is my ozonide.